All right, today's lesson is on special cases of factoring, specifically factoring something called the difference of perfect squares and factoring perfect square trinomials. So, just like we've talked about in previous lessons, when you're factoring, you're basically undistributing. So just like I wanted you to see what happened when you distributed it and when you distributed binomials and how those related to the different types of factoring, I want to do a similar type of process with this lesson as well. So please, for question number 1, go through and do your multiplication. Use the box method for this one, and then press pause and compare with my answer and see how you did. So if you notice in the box, you end up getting x squared minus 4x plus a positive 4x minus 16. And if you were to combine these like terms right here, they actually end up canceling each other out. So these are gone, and you end up getting x squared minus 16. Okay. Question number 2, I want you to do the same thing. Please go through and multiply it on your own. Use the distributive property this time, please, and then compare your answer with mine. All right, so when you go through and you distribute your values here for your two binomials, you'll end up getting 9x squared minus 15x plus 15x minus 25. Now, please double check this because a very common mistake is that people will think this is 3x squared and not 9x squared. So be 100% sure that you said that this was 9x squared. All right. Same thing, we've got some like terms, so we're going to combine our like terms right here. But because one is a negative 15x and one is a positive 15x, those two terms will end up canceling each other out, so they're gone, and that's why you end up getting 9x squared minus 25. Now, as you're doing these examples, you should notice some things that are in common with questions number 1 and number 2. First of all, the binomials are almost identical, except one is a negative and one is a positive. The second term in each set of binomials is a positive and a negative. Also, the middle terms will end up canceling each other out because they're the exact same term, except one is positive and one is negative. And lastly, something that you should really notice, it's super important, is that you end up getting a binomial this time instead of a trinomial. Normally we get trinomials when we have two binomials of the first degree multiplied together. Also, you should notice that in both examples, you will have subtraction signs. So your answer is going to be a difference of two numbers. And more specifically, you should notice that these numbers right here are all perfect squares. They're numbers that can be square rootable. So the square root of x squared is x, and the square root of 16 is 4. And if you notice right here, remember the square root of x squared is x, you have an x right here and an x right here. And the square root of 16 is 4. You've got the 4 here and the 4 here. Okay? Similarly, 9x squared, the square root of 9x squared is 3x, which you have right here and right here. And the square root of 25 is 5, which you have right here and right here. So this is something called a difference of perfect squares. Again, the reason why it's called a difference of perfect squares is because you are taking the difference of two expressions or two terms, and the two terms that you're taking the difference of are perfect squares, and when you factor it, when you work backwards and you put it back into the parentheses right here, you'll end up getting the square root of the first term. In this example, in this general terms, you have a, and the square root of the second term in general terms would be b, with a minus and a positive. Remember, the reason why this has to be a minus and a minus b and a positive b or a plus b is because when you do your carets, those outer and inner terms, negative ab and positive ab, will end up canceling each other out, which is what causes us to have a binomial. So I have this general form down on the bottom so you can see how it's going to be linked to how we factor this. Remember that because this is not a GCF question, we are going to factor it into two binomials being multiplied together. And when I figure out what those two binomials are, I look at the first term and I see what I get when what will multiply together to give me x squared. But remember, it's a perfect square, so the square root of x squared is x. All right, and then same thing with this 9 right here. They have to be the exact same number if it's a difference of perfect squares. So I'm going to put a 3 here and a 3 here. But in order for this to turn into a binomial and for the outer and the inner terms to cancel each other out, this one has to be a positive 3, this has to be a negative 3, and it is factored by a difference of perfect squares. But let's double check to make sure that this is right. So, and remember, when you want to double check, you can just go through and distribute it to see if you end up getting the original problem. So x multiplied by x gives you x squared. When you distribute this x to this negative 3, you get negative 3x. When you distribute this 3 to this x, you get positive 3x. It looks promising because those will cancel each other out. When you distribute this 3 to this negative 3, you get negative 9. So you end up getting x squared minus 9. So I should not have circled that because that's not the final answer. That's just our check to make sure that it's right. So what we have right here is our final answer, and we have factored by difference of perfect squares. Now, question number 4 is a little bit trickier because if you look at it, it's not really in this format where it's a squared minus b squared. It's really negative a squared plus b squared. So what I'm going to do is I'm going to rewrite this in a different order so that I can see this a little bit better and be able to factor it. So I'm going to put the x squared first. Since it's a positive x squared, I just write x squared. And then if I have a negative 9, I'll write minus 9. So then this is the exact same problem as number 3. So I get x plus 3 multiplied by x minus 3. Now you might have noticed that I did mine in a different order than what's written in the general form. The negative sign came first and the positive sign came second. It does not matter which one goes first and which one goes second. If you notice right here, in the two examples that we multiplied together. In this example, the negative sign came first and the positive sign came second, but the inner and outer still canceled each other out. In this example, the positive sign came first and the negative sign came second, and they still canceled each other out. What's key is that this term matches up with this one, and this term matches up with this one, but as opposite signs. If you take a look at question number 5, this question is very tricky, and I really want to discuss this more in depth with you all next time I see you in class. But I just want you to notice this x squared plus 16 right here. It is not a difference of perfect squares because it does not follow this format. Although it is a binomial, it is a sum of perfect squares. It's not a difference of perfect squares, which is actually not factorable, which means that it makes the expression a prime expression. I want to discuss this a little bit more in detail next time I see you in class. Before we do question number 6 in our paper in front of us, I want to talk really quickly about how you can tell what perfect squares are for variables with exponents. So remember that x squared is a perfect square because x squared is just x multiplied by x. Okay? Now let's try x squared multiplied by x squared. Remember, when you multiply, you add your exponents, so this is x to the 4th power. X to the 3rd, when you multiply that by itself, you get x to the 6th power. So if I want to see what is the square root of x to the 8th power, I know it would be x to the 4th because x to the 4th multiplied by x to the 4th is x to the 8th. So if you notice, any exponent that is an even exponent or a multiple of 2 is square rootable. So another example would be x to the 24th power. I can take the square root of that because x to the 24th is x to the 12th multiplied by x to the 12th. All right, so in looking at question number 6, I want to see to make sure that this is really truly a difference of perfect squares. So if you notice this in this example, it is a binomial. There is a difference. Remember, x to the fourth is square rootable, and 81 is square rootable as well. So it is a difference of perfect squares, which means that I can go ahead and set up my problem so that it is a difference of perfect squares. So the square root of x to the fourth power we just discussed is going to be x to the second power. So that's what goes in the first part of each binomial. And then the square root of 81 is 9. So I get 9 here and a 9 here. Now this is a minus 9. This is a plus 9. So that's what you get when you factor this. Now here's where it gets a little bit tricky. If you look at this expression right here, however, x squared minus 9 is still another difference of perfect squares. So I end up getting x squared minus 9. I'm going to go through and I'm going to factor this x squared minus 9 right here. So I end up getting x plus 3 multiplied by x minus 3, because remember, this x multiplied by this x is x squared. This 3 multiplied by this 3 is 9. One has to be positive, one has to be negative. Then I'm going to copy down the second half of my problem right here, because I can't ignore it. I got to bring that down, and then I can't factor any further, so I am done. One thing that I forgot to mention about this example right here is, just like in this example here, this is not a difference of perfect squares, it's actually a sum of perfect squares, which means that this part right here is not factorable, so I will not break this up. The only one that I could break up was this example right here, or this part of the answer right here. Alright, so that's how you factor a difference of perfect squares. That's one of the two special cases that we wanted to talk about in this lesson. The other special case we will be talking about during our 5A class. Alright, I'll see you guys soon. Bye.